Hello everyone, welcome back to CFD College. I'm Ashkan, and in this video I'm going to solve some questions and problems from chapter 4 of Fluid Mechanics 1, Fluid Mechanics book written by Manson. And this video is part of, I'm going to solve part of assignment C from Fluid Mechanics 1. The course is presented in Concordia University, but I think anyone can use it because these examples are available in any fluid mechanics course. So hope you enjoy it, and let's jump to the assignment. Assignment C of the course has 3 examples of chapter 4. Chapter 4 is easy. That's the reason that we don't have lots of problems, and I think it's the easiest part of the course, much easier than fluid static and the last part, which is flow in pipes. Okay, as you can see, problem number 30 of chapter 4. Here we have a shock wave. Here we have a shock wave. Let me increase the thickness. So this is the shock wave. A shock wave is a very thin layer in a high speed gas flow across which the flow properties such as velocity, density, pressure, temperature, Mach number change from state 1 to state 2. So here V1, V2, P1, P2. T1, T2. And most of the time the velocity decreases. So basically when we have a shock wave, before the shock wave, we have Mach number more than 1, and after that we have Mach number smaller than 1. Okay, let's go back to the problem. We know that V1 is 1,800 feet per second. V2 is 700, and L, the thickness of the shock wave, is 10 to the minus 4 inches. We want to find the average deceleration of the gas as it flows across the shock wave. How many G's deceleration does this represent? Okay. First things first, the general equation of the acceleration in fluid mechanics is A, it's a vector, equals delta V is a vector, over delta T plus V dot grad of V. Okay, so this is the general equation. I always tell the students, please start with the general form. Don't memorize hundreds of formulas, and this way you won't get you don't get confused in the exam because of the stress. Okay, so this is the general form of the acceleration. Here we have ax equals delta u over delta t plus u delta u over delta x plus v delta u over delta y plus w delta u over delta z. And you have the same for a y and a z. You have to change these u to v and w for these accelerations to find acceleration in other directions. Okay, here we only have x direction, so we should work with this one. And since the flow direction is horizontal, there is no v and w, so v and w equal 0. So this term is 0 and this term is 0. And since we are working in steady state, condition, any derivation over time is 0. So we don't have the first term on the right hand side. So it's simple. Ax equals u du over dx. And acceleration equals axi equals u delta u over delta x I. Okay, so we need to find this value. We know the second term, delta u over delta x, which is v2 minus v1 over L. But we don't have anything for u. We can consider u as the v1 or v2. But I think you all agree that a better assumption is to consider u as an average value. So v1 plus v2 divided by 2. Now it's easy. You can find the value. So ax equals v1 plus v2 divided by 2. It's an approximation times v2 minus v1 divided by L. And we know the values. So ax is approximately equal to 1800 plus 700 divided by 2. This is feet per second, and it should be multiplied by 700 minus 1800 divided by 10 to the minus 4, but it's inches, so we should divide it by 12 to have feet, and this is feet per second. So ax can be found as minus 1.65 10 to the power of 11 feet per second square. And now we have to divide it by g. So minus 1.65 10 to the power of 11 feet per second square divided by 52.2 feet per second square. It's equal to minus 5.12 10 to the power 9. So that's it. It's easy. As you can see, it's not difficult. This chapter is really good chapter for the students. Let me solve this problem. solve this issue. Okay, now you can see the second problem number 37. Here in this problem we should investigate a hydraulic jump. In a hydraulic jump, the velocity, through the hydraulic jump, the velocity decreases. As you can see, V2 is smaller than V1, while the depth increases. So Z2 is greater than Z1. A hydraulic jump is a rather sudden change in depth of a liquid layer as it flows in an open channel, as shown in the figure below. In a relatively short distance, thickness L, the liquid depth changes from Z1 to Z2 with a corresponding change in velocity from V1 to V2. V1 is 1.2 feet per second and V2 is 0.3 feet per second, and we know the L, the length on which hydraulic jump is occurred, and we should estimate the average deceleration of the liquid as it flows across the hydraulic jump, and also how many g's deceleration does this represent. Okay, now I think you all know how we should solve this problem. As you know, A equals AX I, because we should neglect the velocity in y direction. We only have velocity in x direction. So A equals, and we du over dt plus u du over dx, delta, plus v delta u over delta y plus w delta u over delta z, since w and v are equal 0 and we are at steady state condition, this term is 0, so A equals u delta u over delta x. And just like previous problem, we know delta u over delta x. We can estimate it, or we can calculate it, by this equation, v2 minus v1 divided by L, and for u we use the same assumption, 1 over 2 v1 plus v2. So A equals v1 plus v2 over 2 times times v2 minus v1 divided by L. So A equals 1.2 plus 0.3 feet per second divided by 2 multiplied by 0.3 minus 1.2 feet per second divided by 0.02 feet, which is L. So A equals minus 33.8 feet per second square, and A over G equals if we take the absolute, 33.8 divided by 32.2, and we have the same units for both, feet per second square. So the absolute value of A over G equals 1.05. This is so easy. And let's solve the third problem here, which is the problem number 46 of chapter 4. Fluid flow past a sphere. So here we have a sphere. We know the upstream velocity V naught is 40 meters per second. This is V naught. And from a more advanced theory, it is found that the speed of fluid along the front part of a sphere, it means from theta equals 0 up to 90, velocity can be found from this equation. Determine the streamwise and normal components of acceleration at point A. We know the radius, which is 0.2 meters. So we want to find the streamwise and normal components of acceleration at point A. Point A has at point A, theta is 40 degrees, and we know the radius of the sphere, which is 0.2 meters. Okay. Here we are working in another component system. So in Cartesian, we had AX, AY, AZ. Here in streamwise coordinates, we have AS and AN. So if this is the streamline, if this is a streamline, we have this AS, the streamwise component, and we have AN, the normal component of acceleration. Actually, this is okay. Let me remove it. So for example, if this is the origin, this curvature, this is R, and here is AS, and you know AN is in the radius direction. Okay, in these coordinates we know that A is AS plus AN. AS can be found as, okay, let me decrease a bit, decrease thickness. AS equals V delta V over delta S, while the normal component equals V2 over R. This is R, the radius of the curvature. Okay, so I think it's not difficult for you. Let's start with the normal component. AN equals V2 divided by R. Here in this example, the radius of the sphere is r, so it equals v square over a. We have to find v equals 3 over 2 v naught equals 40, so 40 meters per second times sine of theta, which is 40 degrees. And sorry, this has the unit of meters per second, and we should yes, we have v square, so we have the power of 2 here, and in the denominator we have the radius, which is 0.2 meters. So the normal component equals 7,440 meters per second square. And what about the streamwise component, which is v delta v over delta s? The velocity we have is a function of theta. As you know, in this example, v is equal to 3 over 2 v naught, which is a constant, sine of theta. So here velocity is a function of theta. We cannot take the derivative of this relation of this formula with regard to s. So we have to change the parameters, the derivative. So as equals v, instead of delta v over delta s, we can write delta v over delta theta and multiplied by delta theta over delta s. We can do it. Now we can solve the problem. As you can see here, we have a v, which is 3 over 2 v naught sine of theta. We know v naught and theta. Delta v over delta theta equals 3.2 v naught cosine of theta, and delta theta over delta s. We have to find this. As you can see here in the sphere, let me draw it again. When we move from this point to this point, here is theta and here is s, and we know that s equals, we can assume that actually s equals the radius times theta. So s equals 0.2 times theta, and the unit is meter. So delta theta over delta s equals, from this we can find that theta equals s over 0.2 meters. So delta theta over delta s here is equal to 1 over 0.2 meters. Now we have all three terms. Now we can solve it. So AS equals velocity. We notice 40 times 3 divided by 2 equals 60. 60 sine of 40 degrees. This has the unit of meters per second. It's velocity. Times this term, delta V over delta theta. 60 cosine of 40 degrees meters per second, and the last term 1 over 0.2 meters. So AS can be found as 8,860 meters per second square. And as you can see, this equation was a bit more difficult, but you can solve it if you know the general equations. Okay, I think it's good for this session. These are 3 questions. We solved them from chapter 4 of Fluid Mechanics 1. In the next video, I'm going to solve some problems from chapter 3. For those who are a student at Concordia University, we have other problems in assignment C, and you have to watch the next video if you want to see how you can solve them. So see you in the next video. Thanks for watching, and if you like these videos, please subscribe to the channel, and please share these videos with your friends. Of course, in the channel I have many videos on CFD and numerical simulations. If you like them, please share them with your friends and you can enjoy them. So until the next video, take care of yourselves and bye bye.